Hi, welcome to That Geometry Show. This is That Show, and I'm Kevin Corpy. I'll be your host throughout the season. Now, today, the first show, we have to kick it off with, of course, what is geometry? What is this stuff we're going to be studying all year long? And then we're going to get into some three basic topics, points, lines, and planes, from which the rest of the geometry curriculum takes off. Now, every week, as I go through these shows with you, I'll be having handouts that I'm going to be writing the information down on. And they're available for you to download from our district website. Today's lesson is Lesson 1, and it goes along with the Chapter 1.2 in the Glencoe book. And even if you're a parent at home watching this, it's a great way for you to see what your kids are doing in class and maybe give them a help with their homework. So, let's go ahead and begin. All right, Lesson 1. What is geometry, points, lines, and planes? Well, I'm going to deviate from the outline a little bit and just talk, and then I'll come back to the outline. Geometry is actually a branch of mathematics that originated as early as 3000 BC in the ancient East by the ancient Sumerians, Babylonians, and the Greeks. They used geometry, although they didn't call it back then, mainly for practical reasons for surveying and construction and astronomy. You see, back then, just like today, land was worth money. And it was a very important job of the people of the day to accurately measure the land and the plots of land that were along the riverbanks. And the method of choice back then that they preferred was the knotted rope. And the knotted rope was basically a long rope that had knots in every certain length, and they would basically map out the plots of land using this rope, and they would count the knots, and that's basically indicative of the size of the land. And of course, the bigger the land, the more that they could tax you on it. So geometry did start off as a very practical branch of mathematics. Now, it wasn't until about 300 BC where it took its first big jump into what you are studying today in class, and that was due namely to a Greek mathematician by the name of Euclid. And the Greeks were kind of a privileged people because Alexander the Great established the library at Alexandria, and they were prosperous, and they could actually philosophize and think about things that didn't require them to think about where they were going to get their next meal. So Euclid basically gets credit for writing the first geometry textbook. So you have him to thank every single day when you go to class, and especially when you open your textbook to do your homework problems. Thanks, Euclid. But anyway, he basically took the willy-nilly approach and the practical approach of the ancient Sumerians, and he started applying some rigorous rules to it. And he came up with this idea of the axiom. And an axiom is basically a principal truth. And today, the axiomatic form of geometry is what you're studying. And I'll talk about that a little more, but let's catch up with the outline here. The Greeks were the people that gave all the names to all the math that was already going on in the ancient world. So geometry did get its name from the Greek geo, which means earth, and from metri, meaning measure. So that's a very appropriate name that they gave it since they started measuring plots of land back in the ancient days. It was developed to meet the practical needs in surveying, construction, and astronomy. Although it did exist as early as 3000 BC in ancient Babylonia, it wasn't until a Greek mathematician named, who is it, kids? Euclid. That's right. He wrote around 300 BC his famous work, and here was the name of his textbook, Elements of Geometry. And actually, it was 13 books, so you're pretty lucky to have it condensed down to one version. Now, that's the geometry that we see today in class. It's the axiomatic form, and an axiom, again, is just a principal truth. So the geometry that we study in high school is appropriately the study of, well, we give him credit, Euclidean geometry. Okay, now basically here's what Euclidean geometry entails. You start with a few undefined or primitive geometric concepts, and we're going to define 3 of those today, and you start with a small set of axioms or these principal truths. And then you proceed to derive all of the geometric results from the past few thousand years through rigorous proof. Sounds pretty easy, huh? Well, although proofs can be quite daunting and quite difficult, Euclid himself said that there's no royal road to geometry. Learning a few practical geometric facts is really of no great effort, and that's what we're going to try to accomplish throughout the year. So today, we're going to learn about 3 undefined or primitive concepts, namely points, lines, and planes. in a two-dimensional environment. Now, it's worth taking a look right here. This is a surviving piece of what Euclid's original elements look like. Look how ancient and old that is. That's written on papyrus. Can you imagine if your textbook today looked like that? It'd be very difficult to do your homework. Well, luckily, we've made improvements upon his math, and so now we're ready to take a look at it. So, here's looking at Euclid. The first thing we're going to define here, the undefined term or the primitive term, is the idea of a point. Now, a point is something that you're probably intuitively familiar with, but the mathematical definition is a point is a geometric element that has position but no extension. That means it has 0 dimensions. When we draw a point, we usually kind of make a dark enough circle so that you or your teacher can see it. But bear in mind that a point is infinitely small. Okay? It is defined by its coordinates on the coordinate plane. And it's represented by a capital letter. A coordinate plane, it's worth talking about that. A coordinate plane, as you see down here, is divided into 4 quadrants with a center, which I'll draw right here, that has a name. It's called the origin. Okay, now a word about the coordinate plane. The first great breakthrough in geometry since Euclid came in the 18th century when French mathematician and philosopher René Descartes was sitting in bed, supposedly, watching a spider move across his wall. And he said, hey, there ought to be a way to describe where that spider is along the wall at any given point. And he came up with the idea of designating a horizontal distance left or right from some fixed point, which we're going to call the origin, and a vertical distance also from that fixed point called the origin. And that's basically what we call our coordinate plane, or sometimes it's called the Cartesian plane, named after René Descartes. Now, the Cartesian plane does have 4 quadrants. These 2 number lines, real number lines, divided into 4 nice quadrants. This is quadrant 1, quadrant 2, quadrant 3 is down here, and quadrant 4 is down here. And we're going to look at the coordinate plane more intensively later on in another show. But right now, it's important to know how we orient ourselves along here. If you've ever read a map and looked up a street and found it to be at, let's say, D6, you're familiar with how a coordinate system works. We basically have to get an ordered pair, a coordinate, 2 ordinates, and we list them as a x-y pair, where the x is the directed horizontal distance from the origin, positive is to the right, negative is to the left, and a directed vertical distance, which we're going to call the y-coordinate, along the vertical or y-axis. Again, positive is up and negative is down. So what I've done here is I've represented 4 different points, A, B, C, and D, in 4 different quadrants. Again, I've shown them large enough so that you could see where they are, but in actuality, they're infinitely small. Now we're going to go ahead and see if we can describe where these points exist using the coordinate system. So point A over here appears to be in quadrant 2. We start with the origin, and we always go horizontally first. I have to go left 1, 2, 3 units, so my x-coordinate is -3 to the left, and then from there I go up 2 units to land on A. So up is the positive direction, so the coordinate of point A is the coordinate, or the ordered pair, -3, 2. And we typically denote it inside parentheses. Okay? Pretty easy. Point B, it's over here in quadrant 1. Let's see how to get there. We start at the origin. It's the UR here, basically. And we're going to go 1, 2, 3 units to the right and up 1 unit. So right 3, up 1. Those are both positive. That's the coordinate 3, 1. Point C down here in quadrant 2, you are here. You've seen it on the mall map. To get to the gap, which I guess can be store C, we have to go left 1 unit and down 1, 2, 3. Those are both negative directions. Left 1 is -1. Down 3 is -3. So point C lies at the coordinate -1, -3. And finally, D, maybe that's the food court. We're getting hungry. We are here. We have to go right 2 units and then down 1 unit to get to D. So right is positive. That's plus. Down is negative. That is -1. So the food court, or in this case point D, lies at the ordered pair 2, -1. All right? Now it's worth noting here that I've already said that points have no dimensions. They're infinitely small. I'm going to go ahead and say that. Points have 0 dimension. Or as I said earlier, they have position, they have a location, an ordered pair, coordinate, but no extension. They don't get big, they're just there. Okay? Now that's a very basic concept. Let's move on, or step it up one dimension now, to something called the line. Okay, now a line is another important undefined term in geometry, or a primitive term. I'm actually going to define a line, but we still call it undefined, meaning primitive. So a line is a one-dimensional object defined by 2 points. You only need 2 points to define a line. So any 2 points on the line, and the line extends indefinitely or infinitely in both directions. It's shown by drawing an arrow at both ends, and it's named by a lowercase script letter, such as M, or by any 2 points on the line. For instance, if I have a line, there's a line that we know and love, but I'm going to put little arrows on either end to show that it extends off into infinity in both directions, although there's no way I'm going to draw that. Now, I can define that line by naming it something like lowercase script m. Any letter will work. Or I can put a point, and again, I'm going to accent the point by drawing it darker and bigger. Call that A, call this B. So I can actually name that line now 3 different ways. I can call it line M. I can call it line AB, and we have to draw basically the symbol for the line, which is the double-headed arrow, above the AB to denote the line. Now, because it goes on to infinity in both directions, the order of the lettering doesn't matter. We can equivalently call that line BA. As long as we put the double-headed arrow, we're talking about the exact same line. Okay? So there's 3 different representations, 1, 2, 3, of the exact same dude. In this case, the line. Now, here's an example 2. List some other possible names for line VZ. So VZ, here's the diagram down here. Hope you can see it all right. VZ, well, we're starting here. There's V, there's Z. That pretty much covers all the points. We can come up with some other possible names. Well, notice the little script letter that's already written by the line. So, of course, some other names for this guy might be line M again. Doesn't always have to be an M. We can start listing from point V on. We can go from V to any other point. Let's go to W here. I can call it VW. And as long as I put the arrow above, that's going to be the same line. I can also flip that around, call it WV, double-headed arrow. We're good. I can go from V to X, double-headed arrow. We got the line. I can, of course, flip that around, XV. So it doesn't really matter what combination of letters I use here. There's actually 20 different combinations if you include the reversing the letters. So that makes 20 plus line M. There's 21 different ways to name this line. Let's come up with maybe a few more and we'll move on. How about a Y? And pick any point. Give me a W. There we go. So YW, as long as I put the arrow above, is a representation of the line. And I've already seen many students this year particularly get careless or maybe not concentrating enough, and when they're naming lines, if the instructions are asking for lines or we're supposed to name a line, we need to make sure we put the double-headed arrows, because you'll see later on without the arrows, it's something entirely different. Okay? Let's move on to example 3. Example 3 says name some lines that lie in plane ADH. Now, we haven't really discussed planes altogether, but a plane is basically just a flat surface. Let's look at ADH. If you look at A, D, and H, and you connected these lines, it would appear to be the side right here of this box. And it says to name some lines that are in this plane. So it's probably helpful to redraw this little side of the box so that we're facing it. And maybe we're facing it from the inside, so I can label it the same way. A, E, D, and H. All right, now we have to take a quick break for some public service announcements, and I know I don't have to tell you not to go away because you're going to be there anyway because you want to know this stuff. So we'll see you back here shortly.
This is a wonderful resource for the district. for the students to come to and the parents to come to, because I can answer those questions on where to start and you know, what's the first step you need to take in order to make college a reality. There's a lot of resources in here. There's a lot of printed material, and of course we have 16 computers, and I recommend don't ever pay anybody to pay for a scholarship search, because those are things that we can do for free, and I can show you how. I had a senior who was not sure that she was ever going to make it to college, and she got into UTSA. I'm so proud of her. She's very successful. I just heard from her recently. She got a very large chunk of financial aid through her research efforts. Come visit us. We're here. We want the word to get out to the community that this is a resource that NBISD provides for our students, and take advantage of it. It's free.
Alcohol kills more kids than all illegal drugs combined. Each day, 7,000 young people under the age of 16 have their first drink.
Twice as many kids use alcohol more than any illegal drug.
3 million kids ages 14 to 17 are considered regular drinkers.
Kids under the age of 21 will spend $5 billion on alcohol.
1 out of every 4 kids live in a home where alcohol is abused.
Alcohol is a key factor in 1 out of 3 divorces.
1/2 of all adults have a family member who is an alcoholic.
It only takes one adult to make a difference.
It's not just about drinking and driving.
It's not about responsible underage drinking.
It is about not starting before the age of 21.
It's all about providing positive coping skills.
It's about weaving a web of support for each child.
All right, welcome back to That Geometry Show. Again, I'm Kevin Corpy, and let's get right back into points, lines, and planes. Let's return to example 3. We've taken the side of the box here, and we've drawn it from the frontal view, and now we're trying to name some lines. Now notice that these are not really lines because they don't extend infinitely in all directions, but we can imagine the line coming through here extending both ways. So we have line AE, and of course we can call that EA as well. We have line EH. We can keep going here. We can call that line DH or HD, doesn't matter. And we have this line here that can extend. We can call that line DA or AD. Now that might appear to be all of them, but you always need to think, in this case, inside the box. We can connect from A to H along the diagonal, and I get another line that can come right in through there. So we can call that one line AH or line HA. And I can do the same thing over here, coming right through, and I get line DE or line ED. So in this case, I have 1, 2, 3, 4, 5, 6 different lines, and of course I can reverse the lettering to get the same line. But notice that these lines are all distinctly different than the lines up here that were all the same line, different names for the same line. Okay, let's move on to the next page. Lines have 2 other close relatives that are not technically lines. The first one is called a line segment. And a line segment is basically a piece of a line that consists of 2 endpoints and all the points in between them. It's denoted by a capital letter of the 2 endpoints with the line above them. For example, XZ. There it is. Without the arrows, it's a line segment. It's a piece of a line that does not extend infinitely in both directions. Okay? So let's look at the figure below. I've got line segment XZ. So X is the starting point, Z is the ending point. So in this case, the length of the segment matters. Very important. For a segment, the length matters. Now, if we started with line segment XZ with just a line above it with no arrows, the equivalent segment is line ZX. It's the exact same segment. It doesn't matter where we start and where we end so long as it's the same location. It doesn't matter which direction we're going. Some other segments up here are WX, which is the same as XW. Those are equivalent segments because they have the same starting and stopping point and they're the same length. But as soon as I change, like if I start at W now and I go to Y, that segment's a little bit longer right in through here. That's a new segment. It is, however, still equivalent to YW. And again, just the line over the top without the arrows means that the length matters and it's a segment. The next close relative is called the ray. And a ray is kind of like a sun ray. It basically is a combination of a line and a line segment consisting of one fixed endpoint, that would be the sun if you're thinking of a sun ray, and extending indefinitely in a direction, in this case towards Earth. It's denoted by listing the fixed point first, very important, then any other point with an arrow above it. For example, in the diagram below, using the same diagram, ray YV. Okay? If I'm starting with Y, that means my ray is beginning at point Y and moving in the direction of V, this way. Okay? And it extends past V towards infinity, okay, or infinitely past that point V. So in this case, Y has to be the starting point, and the arrow that I draw above is kind of a combination of the segment and the line. It's fixed on the starting point, and it extends indefinitely over the other point. Now, is that the same as VY? Well, if I draw the arrow this way, and it's conventional to always draw it from left to right, VY basically starts at V and extends towards Y. That is a different ray, because it is pointing in the opposite direction. So whenever you're doing rays, it's not the length necessarily that matters, because it is infinitely long, but it's the direction that matters. Very important. And you always have to remember to qualify what you're doing above your letters, your 2 points, whether it's a ray, a segment, or a line. Okay? Moving right along to the next page, we're going to step it up one dimension still, and we're going to go to a plane. So we went from a 0-dimensional point to a 2-dimensional line that has length to now a 2-dimensional plane. My bad. A plane is any 2-dimensional surface defined by 3 non-collinear points. And non-collinear just means not on the same line. It can be thought of as a flat surface that extends infinitely or indefinitely in all directions. Planes are usually notated by a capital script letter such as W or as 3 points such as plane ABC. Now this paper on which I'm writing is a representation of a plane, but it's not infinitely large, so it's just a model of the plane. Now, you ever wonder why a tripod in photography has only 3 legs? Wouldn't 4 or 5 be better, right? More legs, more stability? Well, not necessarily true, because basically, if it only takes 3 points to define a plane, a flat surface, there's 1 point on the tripod, there's 2, there's 3. Those 3 points right there define their own unique plane. So that if you did have more legs, that other leg would have to be precisely adjusted to land on that same flat surface. And a tripod's nice because you can set it up anywhere on unlevel surface and create your own plane. So 4 legs, not necessarily the quickest or easiest way to get a level tripod. And we want level tripods and steady tripods so our pictures come out not blurry. Let's look at this example here. How many planes appear in the figure below? Now notice that we have a 3-dimensional object that we're trying to represent on a 2-dimensional plane on a flat surface. So the shading and the way we have it drawn at an angle can help you kind of see the dimensions. Now notice that the face of this purple object has 6 sides. It's called a hexagon. There's also a face on the other side. Now joining the edges from one hexagon to the other, we have representations of planes. So all the flat surfaces, or in this case the sides, are going to represent unique planes. Let's go ahead and count them. I'll try and shade them as we go. I have 1. The next one here is 2. I have the one on the side down here. That makes 3. I have the bottom is 4. I have this one here, makes 5. And then the other one here coming up the side makes 6. Now we don't just have 6, because you can't forget we have the front face, which makes 7, and then the one on the back that closes it off to make 8. So it appears that the purple shape has 8 planes that make it up. What about the yellow plane W that's down there? Well, as you could see, plane BCH, which is all we need to define the bottom plane of that solid, happens to be lying flat on the yellow plane. So we can call that yellow plane plane W, or we can call it plane using any 3 points, B, C, H. But they're equivalent, so we don't need to count it twice. So this figure has 8 planes. The next one, how many planes appear in this figure? Well, the face is a shape that we'll see later on in the year called a trapezoid. And that's one of the sides. So if we just count the sides, we'll count the planes of the flat surfaces. So there's 1, 2, we have 1 along the back, that makes 3. 1 on the side is 4. And is that it? Well, we got to have the bottom, that makes 5. And let's close it off on the top with a 6. Okay? So this has 6 planes composing the shape. And that's basically it, points, lines, and planes. But let's go ahead and sum it up here with a say what. Okay? This is just a review, and we'll call this an extension as well. All right, multiple choice. A picture frame is best modeled by a, okay, picture frame. You got it in your mind? Could it be a line? Well, that wouldn't be a very nice picture to look at. This is one-dimensional. Remember, a line is one-dimensional. A plane, well, a plane is a flat surface. Most picture frames are flat. So that could be it. I'm going to put a check and just analyze the others. A quadrant, well, a quadrant was part of the coordinate plane. So we're going to skip that one. And a point, well, a point is 0 dimensions. 0, let me try that again, 0 dimensions. We want a picture frame which has length and width to be 2 dimensions, so plane is definitely the best choice there. Moving right along here, the intersections of 2 planes could be a. All right, intersections of 2 planes. The next example actually has a nice drawing of what the intersection of 2 flat surfaces could look like. But if you're watching this program, I'm sure you're indoors. Just take a look at one of your walls and either the floor or the ceiling. The wall and the ceiling represent 2 planes that are perpendicular to each other. So follow your wall and follow your line down to where they meet. That's the point of intersection. And follow your eyes back and forth. What do you see? Do you see a line? Do you see another plane? Do you see a single point, or do you see a segment? Well, this is kind of a trick question, because if you're inside, you're probably seeing a segment. Remember, a segment has specific length. And unless you live in a huge, infinitely large mansion, your walls actually stop. But remember that our definition of a plane was one that went on indefinitely in all directions. So if you imagine those walls and the floor, the ceiling, extending into infinity both ways, we would actually have a line. Okay? So the line is the better choice over the segment. Now coming down here again, this one's kind of tricky. We've got the intersection of 2 planes. We have the yellow plane, which is plane Z, or we can call it plane PNM. And we have plane X, which is the purple one. Now, let's look at the answer choices. Which of the following statements is not true? We're looking for the false one. Let's go through and see if each one is true or false. Question A, or selection A. Line, and I'm going to be sure to describe what I'm reading here. Line, NM, is in plane X and is in plane Z. Well, is that true? Here's line MN. Is it in plane X? Well, it appears to be running right through plane X. This is kind of like your wall, and this would be the line that runs along the wall where it meets the floor. Plane Z, then, would be the yellow plane, and it would be the floor. This line, MN, would appear to be in both planes. It's where they intersect. Okay, we established that on the previous example. So this one could be true. Unless I find another one that looks more false than that, I'm going to go ahead and count him as true. Let's go to B. X contains M and K. Well, what is X? X is plane X, contains point M. Well, plane X is the purple plane. Point M is this point right here, which we already said was on the line that was in the plane. But does it also contain line K? Well, look, that's a lower script K. Find it on the diagram. That's the line that runs along the bottom of plane X. So it appears that point M is in the purple plane X, and so is line K running along the bottom. So this guy appears to also be true. Let's come back and look at choice C. Plane X and plane Z intersect in line MN. It has the double-headed arrow. Is that true? Well, guess what? We really established that when we looked at A. Line MN is where the ceiling and the wall meet. So it is true. So if A is true, C has to be true. They can't both be false, assuming only one is. So that means D must be the culprit. Let's see why. Now, MN without the arrows is segment MN. Segment MN and point P are in plane X. Well, let's see. Segment MN is only this long. It extends from here to here. Is it in plane X? Well, yes, because line MN is in X. We know the segment, which is shorter, is also in that plane. So that's in there. What about P? Where's point P? He's over here on the yellow plane. Is he in the purple plane? In other words, is he on the purple wall? The answer is no. He's lying on the floor. So this guy must be our culprit. He's the one that's false. Now, if this said segment MN and P are actually in plane, what would they be in? MN and P are both in plane Z, where Z is basically the yellow plane, the floor. That would have been true. Okay, finishing it up here. How many planes appear below? Now, I hope you're giggling at home because really you can clearly see that there's 3 planes. One's yellow, one's red, and one's blue. These are actually airplanes, which is not the geometric plane we've been talking about. There's also 3 alligators in case you're curious. But why would I even put this down here except for a cheap laugh? Well, remember we've been talking about points, lines, and planes. Let's summarize here. Points, remember, were 0 dimensions. They had location, but no extension. Lines were basically one-dimensional. You can measure their length. Okay, they had one-dimension length. Stepping it up another notch, we had planes, which were 2 dimensions. We can measure their length and their width. And so airplanes, which are another type of planes, they don't just stay flat on the runway the whole time. They actually get airborne. And that would mean they fly around in 3 dimensions. So stepping it up here as an extension, we have points, lines, planes, and the next one would be space. Okay? Space is 3 dimensions. It has length, it has width, and it has height, we can say. Now, we're going to be studying 3-dimensional objects later on in the year when we talk about volumes of objects. But for now, that's it. Okay, well, that concludes today's lessons on point, lines, and planes. It's very important as you go through the year to learn the concepts that we are talking about because there's lots of definitions and terminology in geometry, and if you don't get that down, you don't have any chance of really succeeding. So join me next week as we go over lesson 2, which will be measuring segments, midpoints, and congruence. I know you don't want to miss that. Catch you on the flip side.